Good morning. Let's continue to march with chapter 21. We're down to about three components that affect total peripheral resistance, okay? Now we just did the one about the pressure changes in the blood vessels, the arteries to the capillaries, from the arterial side of the capillary bed to the venous side of the capillary bed, and from the venous side of the capillary bed back to the heart itself. So those are three pressure changes. But now we're going to touch on three components that affect total peripheral resistance. Well, it's going to be vessel length, vessel diameter, and the viscosity, the packed cell volume. Okay? Those are three components that will affect peripheral resistance. Now, how can vessel length be changed? Well, the only way that you can change the vessel length is have more vessels. And that occurs when you put on weight. I ain't talking about 5 pounds or 10 pounds, although that'll do it if it's permanent. 50 pounds, 100 pounds. Then you got vessel length that's going to increase, which is going to increase the total peripheral resistance, which is going to raise your blood pressure and give you hypertension because you're overweight. Okay? So that vessel length can be changed when you put on weight. Now, when you lose weight, the vessel length is going to decrease, as it should. Diameter, well, the vasoconstriction. Vasoconstriction, remember the opposite of vasoconstriction is vasodilation. You cannot force your muscles, your smooth muscles in your arteries to relax. You can relax them by forcing them not to constrict. Sounds silly, doesn't it? But vasodilation is the opposite of vasoconstriction. Vasodilation occurs because vasoconstriction is limited. That's the way that it works. Okay? Now, viscosity is the resistance of blood flow. Resistance of blood flow. We've already touched on this right here. The packed cell volume, the amount of fluid that you have in your blood right there, okay? The amount of nutrients that you have in your blood, the amount of red blood cells that you have in your blood right there, all affect the blood viscosity, okay? Now, where does turbulence in the circulatory system occur? How would plaque affect turbulence? Well, believe it or not, the most turbulence that we have is inside the heart. When blood enters in the vena cava, in the right atrium right there, it's a smooth flow, not much blood pressure, almost down to zero. And it enters into the right atrium, then all hell breaks loose. It is constricted, it is pounded, it is forced out through the aorta, through the left ventricle, so the ventricles have the most turbulence. And remember the roughened endocardium, how rough that sucker is right there? It's certainly not smooth. And plaque can form, well, not plaque, excuse me, a blood clot can form inside the heart itself. Now, if it lodges in the endocardium, then there's a problem that can result in that. But as long as the blood doesn't clot, you're all right. When the blood clots inside the heart, then that's a problem. Okay? How would plaque affect turbulence? Well, that's fairly easy. I can draw that one out here. So, smooth vessel wall. Smooth vessel wall. Laminar flow, the flow of the blood, is not disrupted at all. Smooth flow, smooth flow, smooth flow, smooth flow, okay? Not disrupted at all. But now when plaque is there, when plaque is here, this blood right here that strikes the plaque artery is going to be turbulized. Just made that up. It's going to become turbulent. It's going to start to swirl. It's going to start to swirl right here, okay? And once it swirls right here, it's going to form a thrombus. It's going to form a blood clot. So the plaque causes the formation of a blood clot. Plaque interrupts the smooth laminar flow, normal flow of the blood in the blood vessels right here. I'll write down thrombus up here just for the heck of it. All right. That's the way that plaque interrupts the flow of blood. And where does plaque form? Is it an arterial or is it in a venule? Well, the answer is in arterial. Why is it in an arterial? Because that's where the receptors for the LDLs are, okay? We touched on that last time. Monocytes become foam cells, etc., etc. Okay? Now, finish this following statement. Now, we got to go back to the diagram in here, okay? I got to take this damn thing off. Went to rehab yesterday over at Cannon, Sloop, Cannon, there at that hospital there at Limbo. They fussed at me for wearing my sling. I told them I had to wear my sling because I messed up my shoulder. They checked it out and said, well, you didn't really mess it up. I said, then why does it hurt more? Didn't have an answer for that. So I wore it because it hurt. And when I wear it, my muscles tighten up. So I'm trying to do it without it. Anyway, kind of damned if you do and damned if you don't. Okay, I want to go back to a diagram that we looked at, my figure 21-10. Relationship among vessel diameter, cross-sectional area, blood pressure, blood velocity within the systemic circuit. Okay, 21-10. Now this statement comes from that one. Let's see, let's read through it. Finish the following statement. The further away from the heart the vessel diameter, that's the first 21-10A, I guess. Yeah, vessel diameter right here. Well, the diameter is going to get smaller. The diameter of the blood vessels are going to get smaller. All right? Think of one blood vessel, if you will. From the aorta, it's going to, as it descends, it's going to get smaller and smaller in diameter. Okay? And any arteries, any arteriole is going to get smaller the further away from you get from the heart. Now, if I were to ask you about vein diameter, it's going to get larger as it goes back toward the heart. Okay? But the question right here, vessel diameter is going to decrease. The total cross-sectional area, is going to be the next one right here. And it's going to increase. Look at that big hump there in the capillaries. You got thousands and thousands and hundreds of thousands of capillaries in your body right there. Again, we do not have enough blood to fill all the capillaries at the same time. We really, really don't. You got to keep some of them shut off, those P-cap sphincters. Okay, and we'll touch on what regulates that here shortly. Okay, so the total cross-sectional area increases right here. The average blood pressure is going to decrease from the heart till it gets back to the heart. The average blood pressure is going to decrease. That's the one that we looked at the last time. And the velocity of the blood flow is, in general, is going to slow down. It's going to, in general, slow down. And there's a slight increase when you get to the vena cava right there, but in general, the velocity is going to slow down. That's the way that you answer this right here. Okay. Where's the greatest fluctuation of blood pressure? Well, that's in the aorta. The greatest fluctuation of blood pressure is right when the blood comes out of the heart itself. So the greatest fluctuation of blood pressure is in the aorta. Okay? Explain because that's the difference between the systole and the diastole. That is the closest to the heart itself. That's why the blood pressure changes are the greatest. All right? Hypertension, cardiac ischemia. We'll define hypertension. I will need a definition of hypertension in your answer. Hypertension is a resting systole of 140 or greater. A resting systole of 140 or greater. Okay? Remember, systole is a bigger number. 120/70 is about a normal accepted blood pressure right there. A resting systole of 140 right there is considered to be hypertension. That's probably going to change. It may have already changed right there. Maybe 135. Hell, it may be 130. I don't know. But I don't worry about it. 140 or greater at resting systole is hypertension right here. Ischemia is decreased blood flow to the heart. Well, wait a minute. Ischemia is decreased blood flow to anywhere. Cardiac ischemia is decreased blood flow to the heart itself. Now, how in the world can hypertension decrease the blood flow to the heart? Well, the reason is, with hypertension, a persistent hypertension now, the heart is going to work harder, the muscle is going to get larger. The muscle is going to get larger, especially the left ventricle is going to get larger because it's got more pressure to overcome right there. It's going to work harder and harder, just like any skeletal muscle. It's going to work harder. It's going to increase in size. When it increases in size, it outgrows its blood vessels. When it outgrows its blood vessels, the tissues will starve for oxygen. That's where we get the concept of cardiac ischemia. That's the link between hypertension and cardiac ischemia. Okay? 3 means that substances pass through the capillary walls. All right? Now, I might as well talk to you about 3 ways that diffusion occurs through the capillary walls. Okay? And that's all right with me on 7, just right before you get to 2112. Figure 2112, capillary pressure and capillary exchange right there. That's where the answer to this objective comes from right here. So let's talk about diffusion across the wall itself, okay? Now, diffusion. We know that diffusion is movement of from high concentration to low concentration, all right? Temperature affects it, size affects it right there, permeability affects it right here. So let's just take a look at what our author has right here. Water ions and small organic molecules such as glucose can usually enter or leave the bloodstream by diffusion between adjacent cells. Now wait a minute. Wait a minute right here. Water and small ions. Notice it doesn't say diffusion. It does not diffuse across the capillary membrane, itself, all right? Let's go to a capillary cell just for a few seconds. All right, both flow in this direction right here. We're going to use this when we describe the capillary permeability in just a few seconds. So it says it does not diffuse across the wall. Water has to have a pore to go through because it cannot penetrate that bilayer lipid membrane, okay? So it says between adjacent endothelial cells or through the pores of fenestrated capillaries. All right, so not all of these are locked in. Not all of these are locked in. These continuous capillaries, even the continuous, aren't completely continuous. There are pores in between the capillaries, and water and small ions. An ion will not diffuse across the cell membrane itself because of the bilayer lipid membrane, but it can diffuse through small pores. So water and small ions can diffuse through small pores. All right, that's what I want you to know for one. There are channels. The second one involves channels. Sodium and potassium have channels. Calcium has channels. So I've got diffusion through pores. Diffusion is going to occur right here through pores. I'll put it right over here. One way is through the pores.